Let me ask you something that sounds simple. What does space look like? If you've seen any movie, any documentary, any photograph from NASA, you already have an answer forming in your head. You're picturing it right now, the vast black canvas, the pinprick stars scattered like someone threw salt across a dark table, maybe a galaxy swirling in the distance, beautiful, majestic, serene. And here's the thing, that answer is wrong. Not slightly wrong, not off by a little, catastrophically, fundamentally, bone-chillingly wrong in a way that, once you understand it, will make you look up at the night sky and feel something you've never felt before. Something closer to dread than wonder. Because the reality of how dark space actually is, the true physical, mathematical reality of the darkness we're talking about, is something the human brain is genuinely not equipped to process. We evolved on a small rock with a star 30 million times brighter than the next closest one. We evolved in an environment where darkness meant nighttime, where nighttime meant a few hours, where even then the moon and the stars gave us enough light to see shapes, to navigate, to survive. We did not evolve to understand what it means when darkness has no floor, when darkness isn't an absence of light but a presence of something so vast, so total, so absolute, that the word darkness doesn't even begin to touch it. And that's what we're going to talk about today, not the pretty version, not the sanitized, made-for-TV version, where space is this gorgeous backdrop for human adventure. We're going to talk about the actual physics of cosmic darkness, the kind that reveals something terrifying about the universe we live in, the kind that connects directly to one of the deepest unsolved mysteries in all of science, a mystery that touches on why there's something rather than nothing, why you exist, and what the universe looked like before light itself was born. By the time we're done, I promise you will never look at a dark sky the same way again. Let's start with something that sounds like it shouldn't be a question at all. Chapter 1. The question that broke science. Why is the sky dark at night? Go ahead. Think about your answer. You probably said something like, because the sun has gone down, or because the stars aren't bright enough, or just because that's what night is. Every single one of those answers is wrong, and the reason they're wrong launched one of the most disturbing puzzles in the history of astronomy. A puzzle so simple a child could ask it, and so deep that the answer it eventually forced scientists toward revealed something apocalyptic about the nature of reality itself. This puzzle has a name. It's called Olbers's paradox, and it goes like this. In an infinite universe with stars spread out in every direction, infinitely far in every direction, if you look out into space in any direction, your line of sight must eventually hit a star. It doesn't matter which way you look, up, down, left, right, at any angle whatsoever. If the universe is infinite and uniformly filled with stars, every single line of sight must terminate on a stellar surface. Now think about what that means. If every direction you look ends at a star, then the sky shouldn't have any dark patches at all. The entire sky, in every direction, should be as bright as the surface of a star. Not a little bright, not somewhat lit, blazing, scorching, overwhelmingly, lethally bright. The night sky should look like the surface of the sun, in every direction, all the time, with no gaps, no darkness, nothing but blinding stellar light from every single angle of the celestial sphere. And yet, you go outside tonight, and what do you see? A mostly dark sky with some stars in it. This was recognized as a serious problem, not just by Heinrich Olbers in 1823, but by thinkers going all the way back to Johannes Kepler in 1610, who actually used the darkness of the night sky as an argument that the universe must be finite. Because in an infinite universe, he reasoned, the sky should be bright, it's dark. Therefore the universe is finite. Case closed. Except it's not that simple. And the real answer, the one science eventually arrived at, is so much more disturbing than just, the universe is finite. For a long time, people tried to solve this with what seems like common sense. Stars are far away, distance makes them dim, light follows an inverse square, law, meaning if a star is twice as far away, it appears 4 times dimmer. So obviously stars that are very far away contribute almost no light to the night sky. But here's where the math becomes diabolical. Yes, individual stars get dimmer with distance, but as you look farther out into space, you're also looking at more volume. The number of stars in a shell of space at distance d is proportional to d squared, and the brightness of each star falls off with d squared. Those two factors cancel each other out perfectly, completely, 100%. That means every shell of space, whether it's nearby or a billion light years away, contributes the same total amount of light to the night sky. And if there are infinitely many shells, each contributing a fixed amount of light, the total light reaching you should be infinite, or at the very minimum bright enough to make the sky glow as brightly as a stellar surface. The darkness of the night sky is a paradox, a real, mathematical, physical paradox, and it's not one that can be waved away with common sense. So how do we actually solve it? The modern answer came together over the 20th century, and it involves three separate but connected revelations, each one more unsettling than the last. The first revelation is that the universe is not infinitely old. It had a beginning. We call it the Big Bang. This matters because light travels at a finite speed. Even if there are stars infinitely far away, we can only see the ones whose light has had time to reach us in the roughly 13.8 billion years the universe has existed. There's a horizon, a cosmic horizon, beyond which we simply cannot see, not because there's nothing there, but because the light from those regions hasn't reached us yet. So we're not actually looking at an infinite number of stellar shells, we're looking at a finite bubble of observable universe. The second revelation is that the universe is expanding, and it's expanding in a way that stretches light. When light travels across the universe, the expansion of space itself stretches its wavelength. Visible light gets stretched into infrared. Infrared gets stretched into microwave. The further away the source, the more its light gets redshifted, literally pushed out of the visible spectrum. Stars that are billions of light years away are still sending light toward us, but most of that light arrives in wavelengths our eyes can't even detect. The third revelation is that the vast majority of the universe is, in the deepest sense, empty, and this is where things get truly dark. Because solving Olbers's paradox doesn't make space friendly. It doesn't make it comfortable. It doesn't mean there's a cozy amount of light filling the cosmos just enough to get by. The solution to the paradox reveals that the observable universe is, by any human measure, almost incomprehensibly, suffocatingly dark. Let me show you what I mean. Chapter 2. The Arithmetic of Nothing. Let's do some math together. Not the kind that requires a calculator, the kind that requires a willingness to sit with numbers until they stop being numbers and start being something your gut reacts to. There are roughly 2 trillion galaxies in the observable universe. 2 trillion. Already that number is meaningless to you, I know. It's just a big number, so let's work with it. Each galaxy contains, on average, somewhere between 100 million and 1 trillion stars. Let's be conservative and say the average galaxy has about 100 billion stars. That gives us a total stellar count in the observable universe of somewhere around 200 sextillion stars. That's a 2 followed by 23 zeros, 200 sextillion. That's a lot of light sources, an almost unimaginable number of fusion reactors, each one blasting radiation in every direction at the speed of light, and they've been doing it for billions of years. And yet, the amount of light actually present in the universe, averaged across its volume, is astonishingly, laughably small. If you took all the starlight in the observable universe and spread it evenly across all the space, the average energy density of light in the cosmos would be equivalent to a single 100-watt light bulb illuminating a sphere about 2.5 miles in diameter. Let that land. A single light bulb for a sphere of space 2.5 miles across. But even that framing is misleading, because it implies light is evenly distributed. It isn't. Light is clumped. It clusters around stars, around galaxy clusters. Between those clumps, in the vast empty gulfs called voids, the light density drops to levels so low that if you put yourself in the middle of one of those cosmic voids, you would experience a darkness that has no analogy in human experience. Here's a way to understand the scale of what we're talking about. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. A light-year is about 5.88 trillion miles, so Proxima Centauri is about 25 trillion miles away. The Sun is 93 million miles away. The ratio of those two distances is roughly 270,000 to 1. If the Sun were the size of a basketball, Proxima Centauri would be another basketball sitting about 4,300 miles away. That's the distance between New York and Los Angeles times about 1.5. The space between those two basketballs? Completely empty, completely dark. No atmosphere, no dust, no photons except the ones racing out from those stars and the ones coming in from all directions in the cosmic background radiation. And that radiation, as we'll discuss, is so faint as to be essentially invisible, and that's our nearest neighbour, our closest companion in the void. That's the cozy, nearby, practically in our backyard star. Now extend that to the scale of a galaxy. Our Milky Way galaxy is about 100,000 light-years across. It contains somewhere between 100 and 400 billion stars. Those stars are distributed across a disk that, in the vicinity of the Sun, averages about 1,000 light-years thick. The average distance between stars in the galaxy is about 5 light-years. 5 light-years in every direction of empty space. Even within a galaxy, which is the most densely lit region of the universe, the average distance between stars is so enormous that from any given star, every other star is a pinpoint of light, a tiny distant dot. Not a sun. Not something that lights up a room or casts shadows or allows you to see colour. A dot. Go to the space between galaxies, the intergalactic medium, and things become so much worse. The average distance between galaxies is measured in millions of light-years. The voids between galaxy filaments, the cosmic web of structure, can be hundreds of millions of light-years across, containing almost nothing. The intergalactic medium has a density of about 1 atom per cubic meter. 1 atom per cubic meter. These voids are so empty, so dark, so cold, that placing a human being in the centre of one would constitute a form of sensory deprivation with no parallel in our experience. No sound, obviously, because there's no medium for it. No warmth, because the temperature of these regions is only a few degrees above absolute zero. No light from nearby sources, because nearby sources don't exist. The only light arriving would be the cosmic microwave background radiation, and the faint red-shifted glow of distant galaxy clusters, all of it well below the threshold of human vision. You would be, quite literally, in the most complete darkness that exists in the physical universe. But even this description undersells it, because we haven't talked about what dark actually means at the quantum level, at the photon level. We haven't talked about what it means to count the photons in the darkest place in the universe and find out just how few there are. Let's talk about that now. Chapter 3. Counting photons in the void. A photon is the fundamental particle of light. Every ray of sunshine, every beam from a flashlight, every flicker of a candle is made of photons streaming through space. In your everyday environment, photons are everywhere. Right now, trillions of them are hitting your eyes every second. In bright sunlight, around 10 to the power of 17 photons hit every square centimetre of your skin every second. That's 100,000 trillion photons per square centimetre per second. Now let's go somewhere dark. In the darkest place on Earth, a specially constructed dark room with no light leakage whatsoever, the photon count isn't zero. There's still thermal radiation coming off the walls, infrared photons emitted by objects at room temperature. Your own eyes emit infrared. Your retinas, even in complete darkness, are occasionally triggered by random thermal fluctuations. Technically, you can never experience true zero-photon darkness on Earth simply because anything with a temperature above absolute zero radiates photons. But go to space. Go to deep space, far from any star or galaxy. What do you find? The primary source of photons in the deep universe is the cosmic microwave background radiation, the CMB. This is the afterglow of the Big Bang, the relic radiation from when the universe was about 380,000 years old and first became transparent to light. It bathes the entire universe uniformly, coming from every direction. But here's the thing about the CMB, it's incredibly faint. The temperature associated with the CMB is 2.725 Kelvin. That's 2.725 degrees above absolute zero. The peak wavelength of this radiation is in the microwave range, completely invisible to human eyes, and even if you could see it, the intensity is unimaginably low. The photon number density of the CMB is about 411 photons per cubic centimetre. That sounds like a lot until you realise those photons are stretched out, low-energy microwave photons, not visible light photons. In terms of visible light photons in deep intergalactic space, far from any galaxy, the number drops to essentially zero. There are places in the universe where, in a given cubic metre of space, you might go minutes, hours, or longer without a single visible wavelength photon passing through. Minutes without a single photon. Think about your eye. Your eye, the human eye, can detect a single photon under the right conditions. The rod cells in your retina are genuinely sensitive enough to register individual photon impacts. Researchers have done experiments where they've confirmed that humans can detect single photons. But in the dark zones of deep space, you could hold your eye open for hours and detect nothing. Not because your eye isn't sensitive enough, but because there's genuinely, physically, almost nothing there. This is the darkness we're talking about, not a reduction in brightness, not a dimming, a near total absence of photons, a void where the fundamental particle of light is almost entirely absent. Now compare this to the experience of standing on Earth's surface at noon on a clear day. The contrast between what your eye experiences in sunlight and what a hypothetical eye would experience in the deepest void of space isn't a factor of 10. It isn't a factor of 1,000 or 1,000,000. It's a factor of somewhere between 10 to the power of 25 and 10 to the power of 30. That's a 1 followed by 25 to 30 zeros. There is no other contrast of this magnitude in human experience. Nothing we encounter in daily life spans even a fraction of this range. The loudest sound ever recorded and the threshold of human hearing differ by a factor of about 10 to the power of 13. Even the extreme range of human hearing is nothing compared to the range between sunlight and the cosmic void. Space is not just dark the way a room is dark when you turn off the light. Space is dark in a way that has no reference point in human existence, and we still haven't gotten to the most disturbing part. Chapter 4. The Darkness Before Light Was Born. Everything we've talked about so far has been about the universe as it exists today, 13.8 billion years after the Big Bang. A universe full of stars and galaxies and light, even if that light is thinly spread across an incomprehensible volume. But there was a time, not metaphorically but literally, when the universe contained no stars at all, when it contained no galaxies, when it contained no sources of visible light whatsoever. This period is called the Cosmic Dark Ages, and it is the most profound darkness in the history of the universe. Here's how it happened. In the first few minutes after the Big Bang, the universe was a seething plasma of particles and radiation, unimaginably hot, unimaginably dense. Photons couldn't travel more than a fraction of a millimeter before being absorbed and re-emitted. The universe was opaque, like the interior of a star. Paradoxically, it was bright, insanely bright, but you couldn't see anything because light couldn't get anywhere. As the universe expanded and cooled, about 380,000 years after the Big Bang, something remarkable happened. The temperature dropped enough for electrons to combine with protons to form neutral hydrogen atoms. This is called recombination, which is actually a somewhat misleading name because the electrons and protons had never been combined before, but that's what we call it. When this happened, the universe became transparent for the first time. Light could finally travel freely, and that flash of light, that moment of first transparency, is what we observe today as the cosmic microwave background radiation. But here's the dark secret. After recombination, after that initial flash of freedom, the universe cooled further. And what it cooled into was a uniform, dark, featureless mist of hydrogen and helium gas. No stars yet, no galaxies yet, no structure, no clumping, just an almost perfectly uniform fog of atoms, slowly cooling. And that state lasted a very long time. The first stars didn't ignite until somewhere between 100 million and 400 million years after the Big Bang. Some estimates push the first stellar ignition as late as 700 million years post-Big Bang for the first proper galaxies. That means there was a period, a very long period, of somewhere between 100 and 700 million years where the universe contained no stars. No stars means no starlight. The CMB radiation, the only light present, was already being redshifted into longer and longer wavelengths, growing dimmer and dimmer. The universe was cooling, expanding, darkening, and filling with the almost perfectly uniform gas that would eventually become everything we see today. This is the Cosmic Dark Ages, an era of literal, total darkness. Not the darkness of a night sky with stars, not the darkness of a room with the lights off, not the darkness of a cave or a vault or the deepest ocean trench, A universe-wide, all-encompassing, complete absence of light. Stars hadn't formed yet. Galaxies hadn't formed yet. The CMB was there, but it was already at microwave wavelengths, invisible, cold, fading. If you had somehow existed in the cosmic dark ages, with human eyes and a human body protected from the cold, which was a few thousand Kelvin at the start of this era, cooling to a few dozen Kelvin by the end, you would have seen absolutely nothing. A perfect, featureless, total blackness in every direction. Not even a star, not even a galaxy. Just an endless, uniform, cold, silent dark. The universe was empty of light for hundreds of millions of years, and then, out of that darkness, out of that featureless void, gravity began to win. Tiny, incredibly tiny fluctuations in the density of the primordial gas began to grow. Regions that were slightly denser than average pulled in more gas. As they grew denser, they pulled harder. Gas began to flow toward these overdense regions, compressing, heating, spinning. The first clumps of gas were contracting, their interiors getting hotter and denser, approaching a threshold. And then, in one region, and then another, and then millions more, the threshold was crossed. Hydrogen nuclei at the centers of these collapsing clouds reached temperatures and pressures sufficient to begin nuclear fusion. Protons smashed together to form helium nuclei. Energy was released, immense, overwhelming energy. The first star ignited, and for the first time in hundreds of millions of years, there was a point source of light in the universe. A single star, blazing alone in the middle of a cosmos that had been dark since before it was born. Can you imagine it? That single point of light in all of the vast, dark, silent universe. And then more, and more. Stars igniting in clumps and clusters. The first proto-galaxies forming, lighting up like sparks in a dark field. The epoch of reionization, as these early stars and galaxies began to ionize the surrounding intergalactic medium, burning away the cosmic fog and making the universe increasingly transparent. The universe's lights were turning on, but they were turning on in a universe so vast, so incomprehensibly large, that even with hundreds of billions of galaxies, each containing hundreds of billions of stars, the average light density never rose above what we calculated earlier. One light bulb for a sphere 2 miles across. The darkness won. It always wins. There's just too much space, and not nearly enough light, and that leads us to something even more disturbing. Something that takes all of this and makes it worse. Because the universe isn't just dark. The universe is getting darker. Measurably, inexorably, physically darker. And the reason why is one of the most terrifying discoveries in the history of science. Chapter 5. Dark Energy and the Darkening Cosmos. In 1998, 2 teams of astronomers were doing what seemed like fairly straightforward work. They were measuring the distances and velocities of extremely distant supernovae using a particular type of supernova called a Type 1a supernova as a standard candle, a light source of known brightness that can be used to determine distance. The goal was to measure the rate at which the universe was expanding, and crucially, how that rate was changing over time. The prevailing assumption, grounded in decades of theory, was that the expansion of the universe should be slowing down. Gravity is an attractive force. All the matter in the universe pulls on all the other matter. Since the Big Bang, the universe has been expanding, but gravity should be putting the brakes on that expansion, gradually decelerating it. What the teams found instead was so unexpected, so dissonant with everything they thought they knew, that both groups spent months checking their data, looking for errors, looking for systematic biases, trying to find any explanation other than the one the data seemed to be screaming at them. The universe's expansion isn't slowing down, it's speeding up. The universe is accelerating in its expansion. Every second, the galaxies of the universe are flying apart not just fast, but faster than they were a second ago. And a second before that, they were flying apart slower than they are now. The rate of expansion is increasing. This means something profound and deeply disturbing about the future of the universe. And it explains why the darkness we're already experiencing is only going to get worse. The cause of this accelerating expansion is called dark energy. We don't know what it is. Let me say that again, clearly. We do not know what dark energy is. We know it exists because we can see its effects. We know it behaves like a property of space itself, a kind of energy inherent in the vacuum, present everywhere, constant in density even as the universe expands. We know it makes up about 68% of the total energy content of the universe. We know it's the dominant force shaping the future of the cosmos. But what it actually is, at a physical, fundamental level, we have no idea. It's one of the deepest, most embarrassing gaps in all of physics. We have named something we cannot explain and declared it the primary ingredient of the universe. Here's what dark energy means for the darkness of space. As the universe expands, the distance between galaxy clusters increases. Because dark energy is causing this expansion to accelerate, distant galaxies are receding from us faster and faster. Many galaxies that are currently observable are already receding from us at speeds greater than the speed of light. Not because they're moving through space faster than light, but because the space between us and them is expanding, and when enough space is expanding, the cumulative expansion rate can exceed the speed of light. This means that light from those galaxies, light that is currently heading in our direction, will never reach us. The space it's trying to cross is expanding faster than the light can traverse it. Those galaxies will become permanently invisible, and as time goes on, this horizon of permanent invisibility shrinks. More and more galaxies cross over the edge of our observable universe. Their light, already on its way to us, gets stretched into longer and longer wavelengths, becoming redder, dimmer, and eventually so redshifted as to be effectively undetectable. In about 150 billion years, astronomers in our galaxy, if any exist, will look out at the universe and see only our local group, the cluster of about 50 galaxies that includes the Milky Way and Andromeda. Everything else will be gone. Not gone as in destroyed, gone as in receded past the horizon of the observable universe, made permanently invisible by the relentless expansion of space. And then, on even longer timescales, as the stars in the local group age and die, as the fuel of nuclear fusion runs out star by star, the darkness will deepen further. Red dwarfs, the longest-lived stars, will persist for trillions of years, but eventually they too will exhaust their hydrogen and cool into black dwarfs, cold, dark, invisible remnants orbiting in the dark. On timescales of 10 to the power of 14 years, roughly 10,000 times the current age of the universe, the last stars will die. The universe will go dark in a way that makes today's darkness look like midday. No more fusion, no more starlight, just cold, dark stellar remnants, black holes slowly evaporating via Hawking radiation, and the deep, cold, expanding void. This is called the heat death of the universe, or the dark era, and it's not a speculative fringe idea. It's the mainstream scientific prediction for the long-term future of the cosmos, assuming dark energy continues to behave as it does today. The universe is in a brief, cosmically speaking, window of light. We exist in the one era when stars shine. Before us were the Dark Ages. After us will be a deeper darkness still. We are impossibly living in the lit moment of cosmic history. And even in this lit moment, space is almost entirely dark. So where does that leave us? Let's zoom in. Let's come back from the scale of the cosmos and ask a more uncomfortable question. Let's ask about the darkness not as an abstract cosmic fact, but as something that might be trying to tell us something. Something about our place in the universe. Something about what it means to exist. Because there's a way of thinking about cosmic darkness that most science videos never quite reach. A way that connects the physics to something almost philosophical. And I think you need to hear it. Chapter 6. The Darkness as Information. Here's a reframing of everything we've discussed. The darkness of space isn't just a backdrop. It isn't just an absence. The darkness of space is one of the most information-rich facts in the universe. It tells us things, profound, disturbing, strangely beautiful things. The darkness tells us the universe had a beginning. That's what Olbers's paradox ultimately resolved to. If the sky is dark, the universe is not eternal and infinite, and filled with infinite stars. The sky is dark because there was a moment when it all started, and light from the far reaches of the universe simply hasn't had time to arrive. Every time you look at the dark sky, you're looking at evidence for the Big Bang. The darkness is the fingerprint of creation. The darkness tells us the universe is expanding. The redshifting of starlight, the mechanism that helps explain why even the light that has had time to reach us is dimmer than Olber's mathematics predicted, is direct evidence that space is stretching, that galaxies are moving apart, that the universe is not static, not eternal, not permanent, it's dynamic, it's changing, it's running a process with a beginning and presumably an end. The darkness tells us we're alone in a way we might not be comfortable acknowledging. This is the uncomfortable part, the part that gets into territory most popular science avoids because it's too stark, too bleak, too devoid of the comforting narrative that the universe is alive with possibility and the cosmos is full of life and we're part of a great interconnected web of existence. Look at the numbers. The observable universe is 93 billion light-years in diameter. It contains roughly 2 trillion galaxies, hundreds of sextillions of stars, and by extension, a likely enormous number of planets. The sheer scale of it seems to imply that life must be everywhere, that intelligence must be common, that we must be swimming in a universe teeming with other minds. And yet, we have found no evidence of extraterrestrial life. None. Not a signal, not a microbe, not a ruin, not an artifact, not one example of life anywhere other than Earth. And the universe is 13.8 billion years old. Civilizations that arose a billion years before us would have had a billion years to spread, to build, to signal. In a universe 93 billion light-years across with hundreds of sextillions of stars, we have detected the work of exactly one technological civilization. The darkness isn't just physical, it's informational. The silence and the darkness of space converge into a single, disturbing message that we don't fully know how to interpret. Either life is so extraordinarily rare that we may well be the only technological civilization in the observable universe, which is staggering, or something happens to civilizations before they can make themselves detectable, which is more staggering still, or our understanding of the universe is missing something fundamental. The darkness of space looks different when you think of it this way. It isn't just empty, it's quiet, it's watching, it gives nothing back. We send light into it, literally and metaphorically, our radio signals and laser pulses and deep space probes, and the darkness swallows it all without reply. There's a reason the night sky has inspired dread in people throughout history. Not just wonder, dread. The ancients filled it with gods and monsters not just because they were pre-scientific, but because some part of the human nervous system correctly identifies the night sky as something vast and indifferent and not oriented toward our survival. They were right to be afraid, just not for the right reasons. The actual reason the dark sky should evoke something deeper than comfort is the physics, the thermodynamics, the cosmology, the silence, all of it pointing in the same direction. We are on a lit rock, orbiting a middle-aged star in a universe that is 99.9999% darkness, that began in darkness, that will end in darkness, and that currently hosts the brief, thin, statistically miraculous phenomenon of life and consciousness in exactly one known location. The darkness isn't just around us. In some deep sense, the darkness is the default state of the universe. We are the anomaly, we are the exception, we are the brief, inexplicable spark in a void that extends in every direction without end. And I think that's worth sitting with. Not despairing about, necessarily, but sitting with. Really sitting with. Because once you understand the scale of the darkness, once you do the math and look at the photon counts, and read the predictions about the heat death and feel the weight of the cosmic dark ages in your chest, the fact that you exist at all becomes something different. Something that used to feel ordinary becomes extraordinary. Something that used to feel like a given becomes a miracle of probability. You are a collection of matter that has organized itself into a system capable of contemplating the darkness around it. In a universe that is overwhelmingly, cosmically, irreversibly dark, you are lit from within. That's the first thing the darkness teaches. But there's more, because we still haven't talked about the strangest darkness of all, the one that isn't in deep space or between the galaxies or in the era before stars. The strangest darkness in the universe is inside a black hole, and what happens there makes everything else we've discussed look gentle. Chapter 7. The Darkest Objects in the Universe. Let's talk about black holes, not the Hollywood version, not the swirling, dramatic, lens flare-wrapped monsters of science fiction. The real thing, the mathematical, physical, deeply strange reality of what a black hole actually is, and what the darkness inside one actually means. A black hole is a region of space-time where gravity is so strong that nothing, not matter, not radiation, not light itself, can escape once it crosses a boundary called the event horizon. The event horizon isn't a physical surface. There's no wall there, no membrane you'd feel if you crossed it. It's a mathematical surface, a point of no return. Cross it and your future light cone, the set of all possible futures available to you, is entirely contained within the singularity. Every path forward leads inward. You cannot escape, not because you lack the technology or the speed, but because there is no direction outward from inside the event horizon. Space itself has, in a sense, become one-directional. The darkness inside a black hole is different in kind from every other darkness we've discussed. Outside a black hole, in deep intergalactic space, the darkness is an almost absence of photons. It's a near zero photon count. It's emptiness. Inside a black hole, photons exist. Light can be produced inside the event horizon. If you crossed the event horizon with a flashlight, the flashlight would still work. It would still produce photons, but those photons could never reach the outside universe. Every photon produced inside the event horizon travels toward the singularity, regardless of the direction it's aimed. It's not that the light is absorbed or reflected, it's that the geometry of space-time inside the event horizon curves all future directed paths inward. Light aimed outward travels outward for a moment, but space-time curves it around and eventually pulls it inward anyway. From outside the black hole, the interior is perfectly dark. Not a single photon emerges from beyond the event horizon. This is why we call them black holes. They are literally perfectly black. They absorb all electromagnetic radiation and reflect none. But here's where it gets strange. Black holes aren't completely dark. In 1974, Stephen Hawking showed, through a calculation combining quantum mechanics and general relativity, that black holes should emit radiation, not from inside the event horizon, but from right at the boundary, through a quantum mechanical process involving virtual particle pairs. Near the event horizon, quantum fluctuations in the vacuum constantly produce pairs of virtual particles, a particle and its antiparticle. Normally these pairs annihilate each other almost immediately, but right at the event horizon, sometimes one particle falls inside and the other escapes. The escaping particle carries energy away from the black hole. The infalling particle effectively carries negative energy in, reducing the black hole's mass. The result is that black holes slowly evaporate. They radiate, very, very faintly. The temperature of this Hawking radiation for a stellar mass black hole is something like 10 to the negative 8 Kelvin, 8 orders of magnitude below the temperature of the cosmic microwave background. No detector we've ever built could measure it. No detector currently conceivable could measure it. It's the coldest, faintest thermal radiation in the universe. But it exists, and over incredible timescales, it causes black holes to slowly shrink, to slowly give back the mass they've swallowed, to ultimately, after timescales of 10 to the power of 67 years for a stellar mass black hole, or 10 to the power of 100 years for a supermassive one, explode in a final burst of radiation. In the deep future of the universe, in the dark era when all stars have died and galaxies have dissolved, the last things emitting any radiation at all will be the slowly evaporating black holes, tiny glacial flickers of Hawking radiation in a universe otherwise completely dark, cold, and silent. And then those too will end, and then there will be nothing left to produce light, ever again. The universe will be truly, finally, permanently dark. But let's not jump that far ahead yet. Let's stay with black holes for a moment, because there's something about them that connects to the darkness in a way that most discussions miss entirely. When we say a black hole is dark, we tend to mean dark in the visual sense. No light escapes. Fine. But black holes are dark in another sense too, a sense that's conceptually deeper and more disturbing. Black holes are dark informationally. The information paradox is one of the greatest unsolved problems in theoretical physics. When matter falls into a black hole, all the complex detailed information about that matter seems to disappear. A star can collapse into a black hole, and the black hole, according to general relativity, is completely described by just 3 numbers: its mass, its charge, and its angular momentum. Everything else about the star, its composition, its structure, the arrangement of its atoms, all of it seems to be gone. But quantum mechanics says information cannot be destroyed. Ever. This is a fundamental postulate of quantum theory. The universe is a closed system, and information is conserved. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any future or past time. Information is never created or destroyed. Black holes seem to violate this. They seem to be cosmic information shredders. Matter goes in, information comes out as featureless thermal radiation that carries no specific information about what fell in. This contradiction between quantum mechanics saying information is conserved and general relativity saying black holes destroy information is called the black hole information paradox, and we haven't resolved it. Despite decades of work by the best minds in theoretical physics, including Hawking himself, who eventually changed his position on it, we haven't fully resolved the question of what happens to information inside a black hole. There are candidate solutions: holography, the idea that the information is encoded on the event horizon itself; firewalls, a proposal that the interior of a black hole is actually a seething wall of radiation rather than a calm void; island formulas from recent string theory adjacent work. But none of these are settled science. The darkness inside a black hole may be concealing something so deep about the structure of reality that understanding it would require a unification of quantum mechanics and gravity, the two pillars of physics that currently refuse to speak the same mathematical language. The darkest objects in the universe are also the most mysterious. The darkness isn't just physical, it's fundamental. It's at the core of our most important unsolved problems, and that makes the darkness of black holes something different from the darkness of intergalactic space. The darkness of empty space is the darkness of absence. The darkness of a black hole is the darkness of the event horizon, the darkness of information lost, the darkness of a physical regime where our best theories break down and we honestly, genuinely don't know what's happening. There's a kind of intellectual humility forced on you by black holes that no other phenomenon quite manages. When you look at a black hole, you're looking at the edge of human understanding. Beyond that boundary, literally, our physics stops working. General relativity predicts a singularity, a point of infinite density where the equations break down entirely. Quantum mechanics hasn't been reconciled with this regime. We don't know what's actually at the center of a black hole, in the same sense that we don't know what happened before the Big Bang. The darkest places in the universe are also the places where our knowledge ends. That's not a coincidence. It's telling us something. Chapter 8. The darkness we cannot see. We've been talking about darkness as the absence of visible light, but the universe is full of a different kind of darkness entirely. One that doesn't involve light at all, one that's woven through everything, present everywhere, and completely invisible not just to our eyes but to every instrument we've ever built. Dark matter. Dark matter is the name we've given to whatever accounts for about 27% of the total mass energy content of the universe. It doesn't emit light. It doesn't absorb light. It doesn't interact with light in any way that we can detect. It's dark, not in the sense of being in a dark place, but in the sense of being fundamentally invisible, fundamentally non-luminous, completely disconnected from the electromagnetic force that governs how light and matter interact. And yet we're certain it's there. The evidence for dark matter is overwhelming and comes from multiple independent directions. The first piece of evidence came from studying galaxies. When astronomers measured the rotation rates of spiral galaxies, they found something deeply wrong. In a normal disk of matter, like the planets in the solar system, objects further from the center should orbit more slowly. Mercury zips around the Sun in 88 days. Neptune takes 165 years. This is Kepler's third law, a direct consequence of how gravity works in a concentrated mass distribution. But galaxies don't behave this way. Instead of slowing down at larger distances from the galactic center, the orbital speeds of stars in spiral galaxies stay roughly constant, or even rise as you go further out. The rotation curves of galaxies are flat when they should decline. The only explanation that works is that there's additional mass in the outer regions of galaxies, mass we can't see, mass that doesn't emit or absorb light, but mass that contributes gravitationally. A huge halo of invisible matter surrounding every galaxy, extending far beyond the visible disk, providing the gravitational scaffolding that explains the flat rotation curves. Vera Rubin, who spent decades carefully measuring these rotation curves in the 1960s and 70s, was doing some of the most important work in astronomy of the 20th century at a time when the astronomical community was slow to take her results seriously. Her data was unambiguous. Galaxies were full of matter we couldn't see. The second piece of evidence comes from galaxy clusters. In 1933, Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies about 320 million light-years away. He measured the velocities of individual galaxies within the cluster using the Doppler shift of their light, and he found that the galaxies were moving much too fast. If the only mass in the cluster were the visible galaxies, the cluster couldn't hold itself together. The galaxies should be flying apart. They're moving too fast to be gravitationally bound by the visible matter alone. Zwicky concluded there had to be additional mass, invisible mass, holding the cluster together. He called it Dunkel Materie, dark matter. He was right, and he was largely ignored for decades. The third piece of evidence is the most beautiful and dramatic: gravitational lensing. Einstein's general relativity predicts that mass curves space-time, and that light travelling through curved space-time follows curved paths. This means that a massive object between us and a distant light source acts as a gravitational lens, bending the light of the background source and creating distorted, arc-shaped, or even multiple images of the background object. When astronomers study galaxy clusters as gravitational lenses, they can measure how much the light of background galaxies is being bent, and then they can calculate the total mass of the cluster from the degree of bending. When they compare this calculated total mass to the mass of all the visible matter in the cluster, galaxies, gas, dust, everything they can detect, the numbers don't match. The visible matter accounts for only about 15% of the mass needed to explain the lensing. The other 85% is dark matter. This isn't a theoretical inference based on dubious assumptions. This is geometry. This is light bending around invisible mass. The dark matter is literally casting a gravitational shadow that we can measure. The most striking example is the Bullet cluster, two galaxy clusters that collided roughly 150 million years ago. During the collision, the visible matter, the hot gas that makes up most of the normal matter in galaxy clusters, slowed down and clumped in the center due to electromagnetic interactions during the collision. But the dark matter, which doesn't interact electromagnetically, passed right through. We can map both the visible matter using X-ray observations and the total mass distribution using gravitational lensing, and they're in different places. The dark matter sailed through the collision and kept going. The gas got stuck. The Bullet cluster is the closest thing we have to a photograph of dark matter. Not of the dark matter itself, which remains invisible, but of the gravitational outline it leaves in the fabric of space. So we know dark matter exists. We know roughly how much of it there is. We know roughly how it's distributed. And we have absolutely no idea what it is. Every particle physics experiment designed to detect dark matter particles directly has come up empty. The Lux experiment, Pandex, Xenon 1T, all of them looking for weakly interacting massive particles, the leading theoretical candidate for dark matter have found nothing. Not a single confirmed dark matter particle has ever been detected. We live inside something we cannot see, cannot touch, cannot detect, but can only infer from the gravitational echoes it leaves on the things we can see. Roughly 27% of the universe is this invisible, dark, unknown substance. And it's not off somewhere else, in the dark voids between galaxies. It's here, it's in this room. Billions of dark matter particles, if they're particles at all, are passing through your body right now. They're passing through the Earth. They're passing through the Sun. They don't interact, they don't notice you. You don't notice them. You are wading right now through an ocean of invisible matter that makes up more than a quarter of the universe's total mass energy content. And we don't know what it is. This is the darkness that isn't in space. This is the darkness that is space, that is matter, that is everywhere and nowhere and invisible and real. The universe is not mostly made of the stuff we can see. The stuff we can see, stars, galaxies, gas clouds, planets, you, me, everything, all of it together accounts for less than 5% of the total mass energy content of the universe. The rest is dark. Dark matter at 27%, dark energy at 68%. Unknown, unseeable, unexplained, pervasive and dominant. We live in a universe where over 95% of what exists is beyond our ability to directly detect. When you think about the darkness of space, about the vast empty voids between galaxies, remember that those voids aren't empty of dark matter. Dark matter halos extend around galaxies and clusters, and perhaps even through those voids. The cosmic web of structure, the filaments and sheets and nodes of galaxy clusters, is traced in dark matter first and visible matter second. The visible universe is a luminous skin stretched over a dark skeleton, and we've only ever seen the skin. The darkness isn't around the universe, the darkness is the universe. Chapter 9. What the darkness sounds like. We've established what the darkness looks like, or rather, that it looks like nothing at all. Let's talk about what the darkness sounds like. The answer, of course, is nothing. Sound requires a medium. Sound is a pressure wave, a pattern of compression and rarefaction in a material substance. You need stuff for sound to travel through. Air, water, rock, metal, all of these can carry sound because they have enough atoms and molecules that can push on each other. Space is not empty, exactly. The interstellar medium, the gas and dust between stars in a galaxy, has a density of about 1 atom per cubic centimetre. The intergalactic medium has a density of about 1 atom per cubic metre. These densities are so low that they make the best vacuum we can create in a laboratory look like a thick soup. The mean free path of a particle in the interstellar medium, the average distance a particle travels before colliding with another particle, is about 10 billion kilometres. That's roughly 66 astronomical units, 66 times the distance from Earth to the Sun. A particle can travel that entire distance without hitting anything. Under these conditions, sound waves, in any conventional sense, simply cannot propagate. You can generate a compression, but before that compression can push on the next atom has moved away. The signal is lost. But here's something interesting. In dense enough regions of space, particularly in galaxy clusters filled with hot, X-ray emitting gas, pressure waves can actually propagate through the gas. The Perseus galaxy cluster, about 240 million light-years away, has been shown by the Chandra X-ray Observatory to have actual sound waves propagating through it. These are genuine pressure waves caused by the central black hole's jets periodically pushing on the surrounding gas. The frequency of these sound waves is B-flat, 57 octaves below middle C. A frequency so low that the human ear can't hear it. A frequency so low that the period of a single oscillation, a single compression and rarefaction, takes about 10 million years. The note has been playing for the age of the universe and has barely completed a handful of cycles. This is the closest thing the universe has to music. An extraordinarily deep, extraordinarily slow, completely inaudible hum propagating through the hot gas of a galaxy cluster, driven by a supermassive black hole blasting jets of plasma into the surrounding medium. Beyond these exceptional environments, space is silent, not quiet, not hushed. Silent in a way that has no analogy in human experience. We evolved in an environment full of sound. Wind, rain, animals, other humans, the rustling of leaves, the crack of breaking wood. Silence, for humans, is never truly silent. There's always something. The sound of your own breathing, your heartbeat, the slight ringing of tinnitus in a quiet room, background noise from distant traffic. In space, if you could somehow be present and conscious without a spacesuit, stay with the thought experiment, there would be nothing. Not the absence of loud sounds, not the hushed atmosphere of a library. Nothing. Absolute, complete, total silence. No vibration of any kind reaching you through any medium, because there is no medium. Combined with the darkness we've described, this produces a sensory environment that the human nervous system is not designed to process. We are social animals evolved for an environment rich in sensory information. Light, sound, touch, smell, all of these flow to us constantly, and our brains process them, interpret them, build models of the world from them. Remove all of that. Not gradually, not partially, completely. The scientific research on sensory deprivation is instructive here. In float tanks, where people lie in water at body temperature in complete darkness and silence, most people begin experiencing hallucinations within the first hour. The brain, deprived of external input, begins generating its own. Patterns in the noise, voices in the silence, light in the darkness. The brain cannot tolerate a total absence of information. It starts manufacturing experience because experiencing nothing is somehow worse than experiencing a hallucination. In deep space, in the true void, the darkness and silence would be so complete that the brain would likely go to extraordinary lengths to generate internal experience, because external experience would be completely unavailable. The terror of it isn't hypothetical, it's physiologically grounded. We are not built for this. Our nervous systems are incompatible with the baseline state of the universe. The universe's default condition is a sensory environment hostile to consciousness, not because it's trying to harm us, but because it's indifferent. The darkness and silence of space aren't aimed at anything. They're just what's there. They're the texture of reality when there's no star nearby, no planet, no living thing to complicate the void. And the living things, the stars and planets and creatures and civilizations, we're the anomaly, remember? We're the local exception to a rule that runs for billions of light years in every direction. The universe is dark and silent. We are the patch of noise and light in the middle of it, brief, localized, and inexplicably organized. Chapter 10. The Pale Blue Dot and the Scale of Lonely. On February 14, 1990, the Voyager 1 spacecraft was about 6 billion kilometers from Earth, past the orbit of Neptune, heading out of the solar system. The mission scientists had decided to turn the camera back for a final look at the solar system. Carl Sagan had lobbied for this. He wanted a photograph of Earth from that distance. NASA was skeptical. There was nothing scientifically useful about such an image. Earth would be a tiny dot, a point source of light, lost in the vastness. But Sagan persisted, and they took the photograph. When the image came back, Earth was a pale blue dot, a fraction of a pixel suspended in a ray of scattered sunlight. Carl Sagan's response to this image has become perhaps the most famous meditation on human smallness ever written, the pale blue dot. But there's something about Sagan's response that I want to examine from the perspective of what we've been discussing. He wrote about how every human being who ever lived, every king and peasant, every mother and child, every inventor and explorer and destroyer and builder, lived and died and loved and hated on that dot. That all our history, all our suffering and glory played out on a mote of dust suspended in a sunbeam. This is true, and it's humbling, and it's been quoted thousands of times as a call to perspective, to humility, to recognizing our small place in a large universe. But here's what Sagan didn't quite say, or at least didn't emphasize in that particular passage. The dot isn't just small. The darkness around it isn't just big. The darkness is so extreme, so complete, and so indifferent that the existence of the dot in the first place is one of the most improbable seeming facts in the cosmos. Voyager 1 at 6 billion kilometers from the Sun is still in the relative vicinity of the Sun, still in the solar system technically. The next star, Proxima Centauri, is 4.24 light-years away, which is about 40 trillion kilometers. Voyager 1 travelling at its current speed would take about 73,000 years to reach Proxima Centauri. And in that entire space, the 40 trillion kilometers between the Sun and the nearest star, mostly nothing, mostly darkness. The outer Oort cloud of comets, then even those thin out, and then an enormous gulf of pure, dark, cold, silent void. And from inside that void, looking back, the Sun is just a star. A bright star, yes, the brightest in the sky by far, but a star. A point. And Earth? Earth wouldn't be visible at all. At Proxima Centauri's distance, Earth is simply too small and too dim, and too close to the glare of the Sun to see with any technology we currently possess. We are invisible from the nearest star. The nearest star, our presence in this universe, our civilization, our 5,000 years of recorded history, our billions of lives, our technology, our art, our wars, our love. From 4.24 light-years away, we are a whisper inside the glare of a star. And from the edge of the observable universe, we are nothing at all. We are less than nothing. We are far below the threshold of detectability. The darkness is the context in which we exist. And when you really internalize that context, really feel it rather than just understanding it intellectually, something shifts. The scale of the darkness isn't an argument for despair, though you might initially read it that way. I think it's something more interesting. The darkness is the measure of what we are. We are the only things in the observable universe that know about the darkness. You, reading this, are one of the only things in the cosmos that can understand what a void is. Stars don't understand voids. Black holes don't understand voids. Galaxies don't understand voids. They don't understand anything. They're just mass and energy doing what physics tells them to do. We understand the void. We can measure it, describe it, feel awe and dread in response to it, write about it, think about what it means. We are the universe's way of looking at itself, of being afraid of itself, of finding itself strange and beautiful and terrifying. That capacity, that consciousness, that weird, improbable loop where matter becomes self-aware and stares into the abyss and feels something, is as remarkable as the abyss itself. Maybe more remarkable. Carl Sagan said our planet is a lonely speck in the great enveloping cosmic dark. He was right. It is lonely. The darkness is real, and the scale of it is real, and the loneliness it implies is real. But lonely isn't the same as alone in the way that truly alone has no awareness of itself. To be lonely, you have to know you're there. You have to know there's a there to be in. You have to have a concept of others, of distance, of the darkness between you and them. We are in the universe the only things we know of that are lonely. And the capacity for loneliness is the capacity for awareness. It's the capacity to reach out across the dark and wonder if anything else is reaching back. That Voyager 1 photograph captures something real. The dot in the darkness is real. But so is the fact that we're the ones who took the picture. We're the ones who looked. We're the ones who felt something when we saw it. The darkness is vast, but we see it. And that's not nothing. It's close to everything. Chapter 11. The Future of Darkness and the Questions We Can't Answer. Everything we've discussed so far, the darkness of intergalactic space, the cosmic dark ages, the darkness inside black holes, the invisible darkness of dark matter, the accelerating expansion driven by dark energy, all of it converges on a picture of the universe that is simultaneously awe-inspiring and deeply unsettling. Let me lay out the picture plainly. The universe is approximately 13.8 billion years old. It began in a state of extreme density and temperature, expanded, cooled, and over its first few 100 million years, produced the first stars and galaxies, ending the cosmic dark ages and filling parts of the cosmos with light for the first time. We are currently in what astronomers call the stelliferous era, the age of stars. This era will last from roughly the Big Bang until about 100 trillion years from now, when the last red dwarf stars exhaust their fuel and go dark. 100 trillion years is about 7,000 times the current age of the universe. We're very early in the stelliferous era. We're at about 0.014% of its total duration. After the stelliferous era comes the degenerate era, roughly 100 trillion to 10 to the power of 40 years, when the universe is populated by white dwarfs, brown dwarfs, neutron stars, and black holes. No nuclear fusion. Essentially no new light production except for the occasional flash from rare collisions. After that comes the black hole era, from 10 to the power of 40 to 10 to the power of 100 years, when protons may have decayed and ordinary matter dissolved, leaving only black holes slowly evaporating via Hawking radiation. After that, the dark era. Everything gone. No black holes, no protons, no ordinary matter. Just photons at near absolute zero energies, positrons, electrons, and perhaps some neutrinos in a cold, dark, expanding universe with no structure and no possibility of structure ever forming again. Entropy has won. The universe is at maximum disorder, and it will stay that way for literally infinite time. This is not a fringe theory. This is not the speculation of pessimists. This is the straightforward extrapolation of known physics. If the laws of physics remain as they are, if dark energy continues to behave as it does, if proton decay occurs as some grand unified theories predict, this is what the universe does. It gets darker and darker and darker until the darkness is the only thing left. Now, sitting with this, what do we do? There are a few ways people respond to cosmological nihilism, to the idea that the universe ends in cold, dark, silent, maximum entropy. The first response is despair. If it all ends in nothing, if the universe is mostly darkness now and entirely darkness eventually, if our existence is a brief, localized thermodynamic fluctuation against a backdrop of oblivion, then what's the point? This is an understandable response, but I think it's a category error. The fact that something ends doesn't retroactively remove its significance. The fact that a fire eventually goes out doesn't mean the fire wasn't warm, wasn't bright, didn't matter to the people gathered around it. The meaning of an experience is in the experience itself, not in its duration. The darkness at the end doesn't reach back through time and extinguish the light that came before it. A universe that had 13 billion years of stars, of chemistry, of biology, of consciousness, of love and music and curiosity and discovery, and then went dark, is not a meaningless universe. It's a universe that meant something while it lasted. The second response is fascination. This is where I personally land. The fact that we can know any of this is staggering. We have figured out the age of the universe, its composition, its history, its future. We've done it with light gathered by telescopes, with equations derived in quiet rooms, with the persistent, cumulative effort of thousands of scientists over centuries. We're a species that has been doing science for maybe 400 years in any recognizable form. We've been on this planet for about 300,000 years. The universe is 13.8 billion years old, and yet we know where we came from. We know roughly what happened in the first few minutes of the universe's existence. We know about the cosmic dark ages. We know about dark matter and dark energy. We know about the fate of black holes and the long cold future of the cosmos. This knowledge is not a small thing. It is one of the most remarkable achievements in the history of the universe as far as we know. Self-aware matter has figured out the shape and history and future of reality. That's unprecedented. That's extraordinary. The darkness doesn't diminish that. If anything, the darkness makes it more remarkable. In a universe that is 99.9999% dark, empty, cold and inert, one tiny corner of it has become organized enough, complex enough, curious enough to look at the darkness and understand it. That is one of the most astonishing sentences you can write about the universe. The third response is curiosity. Because for all we know, we don't know the most important things. We don't know what dark matter is. We don't know what dark energy is. We don't know what happened at or before the Big Bang. We don't know whether the universe is genuinely infinite or just very large. We don't know whether there are other universes. We don't know how consciousness arises from matter. We don't know whether we're alone in the universe. We don't know whether the laws of physics we've measured here apply everywhere and at all times. These aren't minor gaps. These are fundamental questions about the nature of reality, and they're all connected to the darkness one way or another. Dark matter is invisible. Dark energy is unknown. The region before the Big Bang is inaccessible. The interior of a black hole is unreachable. The universe beyond our cosmic horizon is unobservable. The nature of consciousness is mysterious. Every frontier of human ignorance is in some sense a frontier of darkness. The things we don't know are the dark places on the map. And here's the thing about dark places on maps. They're where the interesting stuff is. Every discovery in science is a region of darkness that became light. The darkness of atomic structure became the light of quantum mechanics. The darkness of stellar energy became the light of nuclear physics. The darkness of the universe's history became the light of Big Bang cosmology. The darkness of curved space-time became the light of general relativity. The darkness isn't just where we're ignorant, it's where the next discovery is waiting. And there will be next discoveries. There always have been. The history of science is a history of humans choosing not to be comfortable with darkness, of lighting torches and walking into the unknown and finding out what's there. The darkness of space, the physical darkness of the cosmic void, is matched by the intellectual darkness of the questions we haven't answered yet. And just as the physical darkness is vast beyond comprehension, the intellectual darkness, the space of things we don't yet know, is probably also larger than we can imagine. But we've always been good at making light. Chapter 11, The Speed of Dark. Here's something that almost nobody talks about. When they discuss the darkness of space, and it's something that, once you understand it, fundamentally changes how you think about light, about information, and about what it even means to observe the universe. Light is fast, extraordinarily, almost incomprehensibly fast. In a vacuum, light travels at 299,792,458 meters per second, about 186,000 miles per second. In 1 second, a photon of light can travel 7.5 times around the entire circumference of the Earth. In 8 minutes and 20 seconds, it crosses the 93 million miles between the Sun and the Earth. In 4 years and 3 months, it crosses the 25 trillion miles between the Sun and Proxima Centauri. We treat the speed of light as the ultimate speed limit of the universe. Nothing with mass can reach it. Information cannot travel faster than it. It is the cosmic constant, the number baked into the fabric of space-time itself, But here's what that means for darkness. When a star dies, when its light goes out, the darkness that replaces it doesn't spread instantaneously. The darkness travels at the speed of light. If the sun were to suddenly catastrophically stop shining right now, you would not know for 8 minutes and 20 seconds. For 8 minutes and 20 seconds, the sun would still appear to shine in your sky, because the last photons it emitted before going dark are still travelling toward you. You're always, necessarily, seeing the past. You're seeing light that was emitted minutes or years or billions of years ago, and you are inferring the present from that ancient signal. This means that when we look at the night sky, we are not seeing the universe as it is. We are seeing the universe as it was. Every star you see is a snapshot from the past. The nearest stars a few years in the past, the stars at the edge of our galaxy, tens of thousands of years in the past, the Andromeda Galaxy, 2.5 million years in the past, the most distant galaxies visible to Hubble, billions of years in the past. The night sky is a temporal mosaic. Every point of light is a different moment in time, all arriving simultaneously at your eye. And here's the disturbing implication. We have no idea what the current state of any of those stars or galaxies actually is. Right now, at this exact moment, as you read these words, countless stars we're currently observing have already died. The light we're seeing from them is ancient. The stars themselves may have gone supernova, collapsed into black holes, or simply exhausted their fuel and faded to darkness centuries, millennia, or millions of years ago. We won't know until the darkness their death produced finally travels far enough to reach us. We are surrounded by the ghosts of dead stars. The night sky is not a view of the living universe. It's a fossil record of the universe's past with different layers from different depths of time all superimposed. Some percentage of the stars you can see tonight with the naked eye no longer exist. We don't know which ones. We can't know. The information about their deaths is still in transit, racing toward us at the speed of light, and won't arrive for years or centuries or longer. This is a form of darkness too. Not the darkness of an absence of photons, but the darkness of unknowing. The darkness of a time delay so vast that our picture of the universe is permanently, irreducibly out of date. And it gets worse. The expansion of the universe means that the most distant galaxies we can observe are not only showing us their ancient past, they're showing us a past from before those galaxies had fully formed. We're looking at baby galaxies, proto-galaxies, the first rough structures to condense out of the primordial fog, and the light that's showing us those baby galaxies has been travelling for over 13 billion years to reach us. The galaxies themselves have had 13 billion years to evolve, to merge, to grow, to potentially build solar systems and planets and whatever might live on them. We are completely blind to all of that. We see the infant. We are missing the entire life. The darkness of time is woven through every observation we make of the cosmos. We are not seeing the universe. We are seeing echoes of a universe that no longer exists in the form we're observing. Now think about this from the opposite direction. Right now, at this moment, light is leaving Earth. Light that originated here, from our cities, our television broadcasts, our radar systems, the natural reflected sunlight off our planet's surface. All of it is spreading outward from Earth at the speed of light in an expanding sphere of electromagnetic information. The oldest deliberate radio transmissions from Earth are about 120 years old. That means the sphere of intentional human electromagnetic signals is about 120 light years in radius. Within that sphere, our presence is detectable in principle. Beyond it, we are completely invisible. There's nothing, no signal, no indication, no whisper that Earth exists, that life exists, that anyone is here. 120 light years is a very small bubble. The Milky Way is 100,000 light years across. Our signals have barely dented the galaxy. The nearest stars have received our transmissions. Some of them, the ones within about 60 light years, might have heard us and had time to respond, and if they responded immediately, their response might be arriving now or in the near future. The vast majority of the Milky Way has received no signal from us. We are silent to them. We are dark, and to the rest of the universe, the 99.9% of it beyond the Milky Way, we might as well not exist. Our signals will take millions to billions of years to arrive. By the time they do, Earth may be unrecognizable or gone. We are shouting into a darkness so vast that our shout travels for billions of years before it could reach anyone, and even then it arrives faint beyond detection. The speed of light doesn't just limit how fast we can send information, it limits how visible we are to the cosmos. We are hidden behind a wall of distance and travel time, as invisible to most of the universe as the universe's deepest secrets are to us. The darkness is a two-way mirror. The universe is dark to us, and we are dark to the universe. There's a philosophical dimension to this that I find genuinely haunting. If there are other civilizations out there, and some of them are looking at the sky right now, they might be looking in our direction. They might have telescopes pointed at the patch of sky where the Milky Way is located, where our solar system is an unmappable speck within it. They might be scanning for signals, for biosignatures, for any indication that something interesting is happening over here, and they would see nothing, because our signals haven't arrived yet, because the light carrying information about Earth's biosphere is still in transit, because we are inside the darkness as far as they're concerned. Right now, simultaneously with this moment, beings on a planet somewhere might be concluding that the universe is empty, that they are alone, that the darkness is total and silence is the only answer to their searches, and they might be wrong for the same reason we might be wrong. Not because life doesn't exist out there, but because the darkness and the speed of light conspire to keep us all permanently out of date with each other. Even if the universe is teeming with life, the speed of light might make that teeming invisible. The darkness might persist, not because the cosmos is empty, but because the cosmos is too big and light too slow for the signals to have arrived yet. This doesn't solve the Fermi paradox. It doesn't explain why we haven't detected signals from civilizations millions of years older than ours, civilizations that would have had millions of years to fill the galaxy with signals. But it adds a texture to the darkness that's worth sitting with. The darkness might be partly a conspiracy of geometry and physics. The universe might be less lonely than it looks, and we might simply be too early or too small or too far from everyone else for the silence to mean what we fear it means. Or the silence might mean exactly what the most pessimistic readings suggest. That intelligent life is so extraordinarily, vanishingly rare that in a sphere 120 light years across, there is exactly one civilization, and it's us. Either way, the darkness holds the answer and the darkness isn't giving it up. Let me give you one more angle on the speed of dark, one that brings everything together in a way that should make the hair on your arm stand up. We've talked about how the expansion of space is accelerating, how distant galaxies are receding from us faster and faster, how eventually they'll cross our cosmic horizon and become permanently invisible. Here's what that means for the speed of dark in a very literal sense. Right now, a galaxy 14 billion light-years away is receding from us at roughly the speed of light. Its photons aimed at us are making no progress. They're on a treadmill, travelling through space at the speed of light, but the space between us and them is expanding fast enough to keep the distance constant. Those photons will never reach us. Galaxies beyond that distance are receding faster than light from them can travel toward us. They're permanently beyond our horizon, not because they're moving through space faster than light, but because the space itself is expanding, and their darkness, the darkness that separates us from them, is growing at a rate that makes those regions permanently, irrevocably inaccessible. The darkness between us and those galaxies isn't passive, it's active, it's expanding, it's growing. Every second, a little more of the universe crosses over the horizon and becomes forever dark to us. The dark is spreading, not dramatically, not visibly on human timescales, but physically, measurably, inexorably. The universe we can observe is shrinking. The darkness is encroaching, not from outside, but from everywhere simultaneously, as the expansion of space pulls more and more of the cosmos beyond the reach of our light and our signals and our knowledge. In 150 billion years, astronomers in the Milky Way will look out at a sky containing only the galaxies of the local group. Every other galaxy, every other cluster, every structure beyond our immediate neighbourhood will have been swallowed by the expanding darkness. Not destroyed, not gone in any absolute sense, just unreachable, unseeable, permanently beyond the horizon. The darkness wins in the end. It always wins. Not because darkness is a force that fights against the light, but because darkness is the default, and the light is the temporary exception, and the exception doesn't have the energy to last forever. The darkness is patient in a way that nothing else in the universe is patient. It doesn't need to do anything, it just needs to wait. And it has all the time in the universe, more time than the universe in a sense, because even time in the dark era becomes a meaningless concept when there are no processes, no changes, no events to measure it by. In the final darkness, even time dissolves into something without structure. The darkness is older than light. It will outlast light by an incomprehensible margin. It was there before the first photon, and it will be there after the last one. We live in the middle of it, briefly, improbably, luminously, and that, I think, is the most important thing the darkness teaches us. Not that we are small, we knew that. Not that we are temporary, we knew that too. But that in this specific, unrepeatable, cosmically brief window, the universe managed to produce something that could look at the darkness and understand it, and in understanding it, push the darkness back. Just a little. Just locally. Just for now. Every piece of knowledge is a photon fired into the void. Make as many as you can. Chapter 12. The Architecture of Absolute Nothing. We need to talk about something that scientists mostly avoid discussing in public. Not because it's classified, not because it's too complex, but because it makes even physicists uncomfortable. The vacuum of space is not empty. I don't mean empty in the sense that dark matter is there. I don't mean empty in the sense that the cosmic microwave background is there. I mean the vacuum, the most complete absence of particles that quantum mechanics will allow, the lowest energy state of the quantum fields that pervade the universe, is not empty in any way that your intuitions about empty would recognize. It's boiling. Quantum mechanics tells us that there is a fundamental limit to how precisely we can know certain pairs of physical properties at the same time. This is the Heisenberg uncertainty principle, and its most relevant application here is the energy-time uncertainty relation. You cannot simultaneously know the exact energy of a system and the exact time of that measurement beyond a certain precision. The more precisely you know one, the less precisely you know the other. The consequence is that in any region of space, even in a perfect vacuum, the energy cannot be precisely zero. If the energy were exactly zero at an exact time, you would have violated the uncertainty principle. So the energy fluctuates, it goes up and down. These are not metaphors, these are literal, physical, fluctuations of the quantum fields that fill all of space. These fluctuations manifest as virtual particles, pairs of particles and antiparticles spontaneously coming into existence, borrowing energy from the uncertainty principle, existing for an extremely short time, and then annihilating each other and returning the borrowed energy. They happen everywhere, all the time, in every cubic centimetre of space, constantly. This isn't a theoretical prediction that nobody has tested. We can measure the effects of virtual particles. The Casimir effect is a measurable force between two very closely spaced metal plates that arises because virtual particle pairs can only exist between the plates if their wavelengths are short enough to fit between the plates, while on the outside of the plates they have no such restriction. This creates an imbalance in virtual particle activity that produces a measurable attractive force. The Casimir effect has been measured experimentally to high precision. Virtual particles are real in the sense that they have real measurable effects, and they're everywhere. In the darkest void of intergalactic space, in the interior of a black hole's event horizon, in the space between the pages of this script, there are quantum fluctuations. The vacuum is alive with activity that we can't see, can't hear, can't directly detect, but that is there. The emptiness is not empty. The darkness is not still. Now here's where this gets deeply strange. These quantum vacuum fluctuations have energy, and when physicists calculate what that energy density should be, based on quantum field theory, they get an answer, a very large answer. In fact, when you add up the contributions from all the quantum fields we know about up to the highest energy scales where we trust our physics, you get an energy density for the quantum vacuum that is roughly 10 to the power of 120 times larger than the observed energy density of the cosmological constant, the dark energy that's driving the accelerating expansion of the universe. 10 to the power of 120. That is a 1 followed by 120 zeros. That is the worst prediction in the history of physics. The cosmological constant problem, as this is known, is the discrepancy between what quantum field theory predicts the vacuum energy should be and what we actually observe it to be. The predicted value is 10 to the power of 120 times too big. This isn't just a small error. This isn't a factor of 2 or 10 or even a billion. This is the largest relative discrepancy between a theoretical prediction and an experimental observation in the history of science, by an enormous margin. Why is the observed vacuum energy so incredibly, precisely, almost unimaginably small compared to what quantum field theory predicts? We don't know. There is no known physical mechanism that naturally produces this cancellation. No symmetry that we know of that would explain why the quantum vacuum energy is so close to zero. If you tried to randomly pick a value for the cosmological constant, the probability of it landing within 120 orders of magnitude of zero would be essentially zero, and yet it did. If the cosmological constant were anywhere near the value that naive quantum field theory predicts, the universe would have expanded so rapidly in its early history that no structure would ever have formed. No galaxies, no stars, no planets, no life. The cosmos would be a perfectly smooth, perfectly dark, perfectly featureless void, expanding faster than anything could ever come together. The fact that the vacuum energy is what it is, small enough to allow structure but large enough to cause the observed acceleration, is one of the deepest coincidences in physics. Some physicists invoke the anthropic principle here. The reason the cosmological constant is what it is because if it were different, we wouldn't be here to observe it. Universes with other values of the cosmological constant would be sterile. We can only exist in a universe where the cosmological constant allows our existence. But this isn't an explanation. It's a restatement of the observation dressed in the language of selection effects. Why does a universe compatible with our existence exist at all? The darkness of space hides not just the absence of photons, but the seething quantum mechanical activity of the vacuum, and the inexplicable fine-tuning of the very energy of that vacuum that allows anything to exist in the first place. The void is not simple. The void is not passive. The void is active, fluctuating, finely tuned, and deeply mysterious, and we live inside it. Chapter 13. What astronomers actually see when they look at the dark. Let's come back from the theoretical and the philosophical and look at what actually happens when astronomers point their most powerful instruments at the darkest regions of the sky. Because the experience of looking at cosmic darkness through a telescope produces something that every astronomer I've ever read about describes with a version of the same word: humbling. In December 1995, the Hubble Space Telescope was pointed at a small patch of sky in the constellation Ursa Major. The patch was selected specifically because it appeared completely empty. No stars, no galaxies, nothing visible in that direction. It was chosen to be as dark and featureless as possible. Hubble stared at this patch for 10 consecutive days. Over 100 separate exposures were combined into a single image, and when astronomers finally processed the data and looked at what they'd collected from that tiny, dark, empty-looking patch of sky, they were looking at something that changed our understanding of the universe. The image showed approximately 3,000 galaxies. 3,000 galaxies in a patch of sky, 5.3 million times smaller than the full moon. A patch so small that if you held a grain of sand at arm's length it would cover it. 3,000 galaxies, some nearby and bright, most distant and small, some so far away that their light had travelled 10 billion years to reach the telescope. Some of the oldest, most distant objects ever observed at that time. This became the Hubble Deep Field, and it changed everything because it demonstrated something profound about the darkness of the sky. The darkness between the stars in the night sky isn't empty. It's full of galaxies, not just a few, not scattered and rare. Full, densely, overwhelmingly full if you only look hard enough and long enough. Hubble has since done this multiple times. The Hubble Ultra Deep Field, the Extreme Deep Field, each time pointing at an apparently empty region of sky and revealing thousands upon thousands of galaxies. The darkness between the stars contains more galaxies than there are stars visible to the naked eye. This is disorienting in the best possible way. The thing that looks dark, that looks empty, that looks like nothing, turns out to be full of more light than you can imagine. It's just that the light has travelled so far, has been so redshifted, is spread over such an enormous area of sky that to the unaided eye it's invisible. The darkness is full of invisible light. And the Hubble Deep Fields raised an immediate question. How many galaxies are there, really? If this tiny patch of apparently dark sky contains 3,000 galaxies, what about the whole sky? For a long time, the estimate was somewhere around 200 billion galaxies in the observable universe. Then in 2016, a team led by Christopher Consolis at the University of Nottingham did a more careful analysis, accounting for small, faint, distant galaxies that even Hubble can't see. They concluded that the real number is closer to 2 trillion galaxies, 10 times higher than previous estimates. 2 trillion galaxies, and the vast majority of them are too distant, too faint to be individually resolved by any telescope we currently have. They're there, their light is arriving, but it's so faint and so redshifted that it blurs into the background glow. There's a background glow, by the way. The extragalactic background light. The cumulative light from all the galaxies too faint to individually resolve. If you could see all wavelengths of light, not just visible light, and could remove the foreground light from stars in our galaxy, you'd see this faint uniform glow coming from every direction. The sum of 2 trillion galaxies integrated over cosmic time. It's not very bright. By human standards, it's barely there. But it's measurable, and measuring it has given astronomers another way to count the total light production of the observable universe. And here's the thing that the New Horizons spacecraft revealed in 2020. New Horizons, the probe that flew past Pluto, is now far enough from the Sun and far enough from the zodiacal dust cloud that surrounds the inner solar system to get an exceptionally clean measurement of the extragalactic background light. And what it found was that the actual measured background light is about twice as bright as what the known galaxies would predict. Twice as bright. There's about twice as much light arriving from the deep universe as can be accounted for by all the galaxies we've catalogued. Where is that extra light coming from? Possibilities include a huge population of faint galaxies too small to be individually detected, diffuse light between galaxies from stars that were stripped from their host galaxies during collisions, or, more intriguingly, something we haven't thought of yet. The darkness, when you look at it hard enough, keeps revealing things that weren't supposed to be there. And even the light in the darkness keeps surprising us. Every time we build a better instrument, every time we extend our reach and our sensitivity, the darkness gives up new secrets, new galaxies, new structures, new light sources we didn't know about. The darkness isn't a wall, it's a frontier. And right now, the James Webb Space Telescope is doing what Hubble did, but better, further, deeper. Looking at galaxies so early in the universe's history that they shouldn't, according to our models, quite exist yet. Galaxies that formed surprisingly quickly after the Big Bang, bigger and more structured than theory predicted. The Webb telescope is finding things in the early darkness of the universe that we didn't put in our models because we didn't know they were there. The darkness is being probed, meter by meter, wavelength by wavelength, and every time it gives us something back. Chapter 14. The Emotional Reality of Dark Space. I want to take a step back from the data and the physics and ask a question that might seem out of place in a science video. What does it do to a human being to truly understand this? Not the surface level version, not the pat yourself on the back for knowing that space is big version, but the deep version, the version where you've sat with the photon counts and the void densities and the heat death and the quantum vacuum and the information paradox and Olbers's paradox, and you've let it all sink in properly and you've felt it, not just understood it. Because this isn't neutral information. Understanding the true darkness of space isn't like learning a historical date or memorizing a formula. It changes something in how the world looks, or at least it should. The astronauts who've travelled to space describe something called the overview effect. It's a cognitive shift, a shift in perspective, that happens when you see the Earth from orbit. The overview effect typically involves an overwhelming sense of the smallness and fragility of the Earth, of the arbitrariness of national borders, of the unity of humanity on this small shared world. Astronauts who experience it often describe coming back changed, more environmentally aware, more convinced of the importance of cooperation, less interested in conflict. The overview effect is triggered by seeing the Earth from a few hundred kilometers up, by seeing the thin blue line of the atmosphere against the blackness of space. What would it do to you to truly understand the scale of the cosmic darkness? To not just see the Earth from orbit, but to feel, deep in your gut, the 93 billion light-year diameter of the observable universe, the 100 million year cosmic dark ages, the trillion-year cooling toward the heat death. I've thought about this a lot, and I think it produces something that isn't quite in the existing vocabulary of psychological states. It's not fear exactly, or not just fear, The darkness isn't coming to get you. It's not hostile, it's indifferent. It's not wonder exactly. Well, not just wonder. Wonder implies something positive, something that elevates. The darkness isn't elevating. It's not despair. The darkness doesn't negate the fact that you exist, that you're experiencing this, that the chain of events from the Big Bang to you is extraordinary. I think the honest emotional response to truly understanding cosmic darkness is something more like vertigo, a spinning, groundless sensation of having the floor pulled out from under your assumptions about the nature of reality and your place in it. For most of human history, we've lived in a universe that felt centered on us. Not just geocentrically, though, that too. Human-centered in the sense that the sky was created for us to look at. The stars were for navigation and mythology. The cosmos was a backdrop for the human story. Even after Copernicus, even after we understood the solar system and then the galaxy, there's been a tendency to tell the story of the universe as a story with us in it, as if the billions of years before we arrived were a long preamble to the main event. Cosmic darkness destroys this narrative completely. The universe spent 380,000 years opaque, and then hundreds of millions of years dark before the first star formed. It will spend 100 trillion years in the stelliferous era, most of which will be populated by dim red dwarfs with no Earths around them. And then it will spend an incomprehensible additional time in the degenerate era, the black hole era, and the dark era. Summing up the dark era, the final state of maximum entropy, is essentially infinite time. The period during which stars like our sun exist is a brief flicker. The period during which intelligent life exists on Earth-like planets around such stars, measured in millions of years perhaps, is a flicker within a flicker. We are not the main event, we are not even a side note. We are a fluctuation, a thermodynamic accident of extraordinary improbability, nested in the only moment in cosmic history when the conditions for our existence are met, surrounded on all sides by a darkness that dwarfs our existence in every dimension. And I think understanding this, really understanding it, is actually one of the most important things a person can do. Not because it's depressing, it isn't, ultimately, or it doesn't have to be, but because it realigns priorities in a way that nothing else quite manages. If you know the darkness is that vast, if you know how improbable it is to be here, to be alive, to be conscious, to be capable of asking questions and feeling things and connecting with other conscious beings, then the things that feel important in daily life get rescaled. The darkness tells you, this is rare. The light you are, the brief, improbable, physics-defying fact of your existence, is rare. The other conscious beings you share this planet with, rare. The capacity for any of you to understand the universe you're embedded in, extraordinarily rare. The darkness is the context, and in that context what happens here on this pale blue dot matters more, not less. Every moment of connection, every piece of understanding gained, every kindness exchanged between improbable conscious beings in a dark and mostly empty universe, every single one of these things is something that didn't have to happen, but it did. And in a universe that is 99.9999% dark, cold, empty and inert, that is remarkable beyond what any number can express. Chapter 15. The Darkness as a Mirror. Here's the most unsettling thing I want to leave you with. The darkness of space isn't just out there. It's not just a property of distant voids or the intergalactic medium or the era before stars. The darkness is woven into the very fabric of what you're made of. It's inside you. Your body is made of atoms. Each atom consists of a nucleus surrounded by electrons. The nucleus is unimaginably small compared to the atom as a whole. If you expanded a hydrogen atom to the size of a football stadium, the nucleus would be about the size of a marble sitting at the 50-yard line. The electrons are dots of probability smeared out across the volume of the stadium. What's between the marble and the walls of the stadium? Nothing. Vacuum. Emptiness. You are, by volume, almost entirely empty space. The atoms that make up your body are almost entirely nothing. The solid, the liquid, the tissue, the bone, all of it is atoms, and atoms are almost entirely vacuum. The electrons aren't orbiting the nucleus like planets around a sun. They're quantum probability distributions, clouds of likelihood. The nucleus is a tiny dense speck in a vast emptiness. The reason your hand feels solid, The reason you can't put your hand through a table isn't because your atoms are solid and the table's atoms are solid and they collide. It's because of the electromagnetic force. The electrons in your hand and the electrons in the table repel each other. It's electromagnetism that makes the solid world feel solid, not actual contact between actual physical substance. You're a pattern of forces organized in empty space. You are an arrangement of almost nothing that, through the miracle of chemistry and biology, has become aware of itself. The darkness that fills the cosmic voids is the same darkness that fills the atoms that fill you. Different scales, different contexts, but the same fundamental reality. The default state of the physical universe is emptiness, and the stuff in it is rare, and the patterns in the stuff are rarer still, and the patterns that think and feel are rarest of all. You are a pocket of pattern in an ocean of void. And the void isn't just outside you, it's between your electrons and your nucleus. It's in the space between every atom and every cell in your body. It's in you. The darkness is in you. This might sound like a reason for nihilism. I think it's the opposite. Because the pattern is real, even if it's mostly space. The pattern thinks. The pattern feels. The pattern has experiences that are, within that pattern's own reference frame, absolutely real and absolutely meaningful. The void doesn't experience anything. The darkness doesn't have preferences. It doesn't care about justice or beauty or truth or love. You do. And that capacity, that caring, that experiencing, those preferences exist in you precisely because you're a pattern complex enough to have them. Not despite the void, in some sense because of the void. Because the void is the stage on which the universe played out 13.8 billion years of physics and chemistry and biology until it produced something that could care. The darkness is the canvas. You are one of the first and perhaps rarest brushstrokes. Conclusion. Let's come back to the beginning. I asked you what space looks like. You said dark. You said stars. You said vast. You were right about all of it, just not right enough. Not nearly dark enough. Not nearly vast enough. Space is dark in a way that encompasses almost everything. Physically dark, with photon densities so low that human eyes could float in the void for hours and register nothing. Temporally dark, with hundreds of millions of years of the cosmic dark ages and trillions of years of the coming dark era, bracketing our brief moment of starlight on both sides. Informationally dark, with dark matter and dark energy, making up 95% of the universe's contents and remaining completely, stubbornly, humiliatingly mysterious. Space is dark inside a black hole's event horizon, in a way that takes space-time itself and bends all futures inward, swallowing not just light but information, hiding the deepest contradictions in our physics behind a perfect, absolute black wall. Space is dark in the quantum vacuum that seethes with virtual particles and inexplicably low energy density, fine-tuned to a precision we cannot explain, held at a value that permits our existence by a coincidence that sits at the heart of the worst numerical prediction in scientific history. Space is dark in the vast intergalactic voids, where even individual photons are rare, where the darkness is so complete and the silence is so total that the human nervous system confronted with it would generate its own illusions rather than accept the reality of absolute nothing. And space is dark in a way that is getting darker every second. The accelerating expansion is pulling galaxies over our horizon, one by one, making the observable universe smaller, dimmer, quieter. 150 billion years from now, the local group will be all that remains in the observable sky. And then the stars in the local group will die. And then the darkness will be everything. But here, now, in this improbable moment, in this improbable solar system, on this improbable planet, something very strange has happened. The universe has become aware of itself, not everywhere, not commonly. In one known location, out of all the trillions of possible locations, matter has organized itself into a form complex enough to look outward at the darkness and feel something in response to it. To measure the darkness, to calculate it, to understand it, to be afraid of it, to be awed by it, to write about it and make videos about it and share those ideas with other awareness havings, other patterns of quantum fields in empty space, and together build a picture of what the universe is. That is what you participated in today. You, a temporary pattern of atoms that are themselves mostly empty space. Use the patterns in those atoms to process information about the cosmos that surrounds you, and you updated your model of reality. You made the universe a little more aware of itself. In a cosmos that is overwhelmingly dark, where darkness is the default and light is the exception, you are right now thinking, feeling, existing. The darkness is real. The darkness is vast. The darkness is coming, but so are you. And that, against all probability, against the weight of all that darkness, turns out to matter. Not forever. Nothing is forever. But now. And now is something. It's almost everything.